alveoli, where the actual gas exchange takes place. So the diameter and the length of those alveoli are roughly 100 microns. So this is the actual image of an alveoli. Okay. So you can understand the range of the length scales involved in this type of problems. And due to this wide range of length scales, it is difficult to experimentally understand the transport processes that occur here. I am not saying that experiments have not been carried out on these, but it is difficult. In that respect, modeling of fluid flows and particle transport in this type of networks come into the picture. Okay. So, before going into the details of the model, the first factor that needs to be taken into account is the length scale, as you can understand. So, we can either model the whole system, which is the global scale, or we can model a subpart of those systems, which I have termed here as the local scale. Okay. Based on those length scales, we can adopt different approaches. The first approach is called the Eulerian approach. The Eulerian approach I will discuss in a brief detail, but we have all studied about the control volume approach in mechanical engineering, right? So Eulerian approach is based on the control volume method. The second one is the Lagrangian approach, which is nothing but the control mass approach. Okay, these are technical terms named after different scientists. So the Eulerian approach is the control mass approach. Now both these approaches, these are applied on a global scale. But if we have to use these or use modeling approaches to understand the local processes, then you have to consider modeling at lower length scales, right? So at those length scales, the main model or the very popular model that is used is called the Lattice-Boltzmann approach. And if we go into deeper length scales, like to the atomic scale, then you have to use the molecular dynamics approach, where you can actually model the movements of each atoms and molecules there. And also we have the statistical approaches like Monte Carlo methods and those things. So I will only discuss something about the Eulerian and the Lagrangian approach. So first the Eulerian approach. As I told you, in the Eulerian approach we follow the control volume method. Okay. And we solve the conservation equations for mass and energy. So the first equation here is the conservation of mass. Second one is the conservation of moment. Here in this equation there are no body forces considered, but we can consider those additionally. Okay. Now this plots here. This is an example of a complex network, simplified example of complex network, where there is a main branch and it's divided into a number of different branches there. So this model of the complex network is used to obtain the velocity fields. This plot here shows the velocity field in this network. So what these guys have done, they have considered a fluid flow from this inlet, and the fluid is moving out from these outlets. Okay. And they have obtained the velocity distribution. We can also obtain the pressure drop and those type of characteristics. So you can see here there is a nice boundary layer flow that is established within the channels here. And this plots in the bottom, they are actually the cross-sectional view of the flow field from at these sections A section, B, C, like that. Okay, so you can better understand the flow patterns from here. So these type of modeling can be done using Eulerian approach. So another example is the flow through rocks. So this plot at the left hand side of bottom, these show the phase distribution. By phase I mean in rocks we don't have pure water. So water might be mixed with some different type of fluids. It may be oil or something like that. So those two are different phases. So they have this in this paper they have modeled this is a rock structure with the pores, and they have modeled the fluid flow and the phase distribution, the water and oil distribution in this structure. This is an example of blood flow through some arteries and veins. So this is the CAD model of that. We can obtain the CAD model directly from the the MRI images, CT images. We can directly obtain the CAD files from that or the images from that, and those can be used to simulate the blood flow. So this is the velocity magnitude distribution in the arteries for the blood.
What is the unit velocity?
I have taken this from paper. They have not mentioned there.
So the last one, 500 and then
Yes, it should be millimeter per second or lower than that.
what is the value below that?
Below this one?
This
one? This is 0. From 0 to say 1000 some units we must have. So this is just an example. 1000 meter per second. The unit should be lower. The unit should be lower.
Maybe millimeter.
Maybe. Okay. So the second approach that I talked about is the Lagrangian approach. So what the Lagrangian approach does, it basically tracks different particles and droplets. It is useful in these type of applications. When we suppose I have a solid object and I want to track the movement of that object through a space. Okay, then I can use this type of approach. So it can be used to track the movement of a number of particles or objects. Now I had this video here, but it will not play. I can show you later. So this type of approach has been widely used to model sprays like water spray, gas spray, those type of things. Also, during the pandemic, the COVID pandemic, it has been widely used to model the transport of droplets that are ejected from the mouth. Okay, so this is an example from there. So this is one infected individual who is ejecting some infected droplets, and how these droplets are being transported in an enclosed space. So these type of models can be done using this Lagrangian approach. Also, there is something called crowd dynamics. Crowd dynamics mean how a number of people. So I had this video from crowd dynamics here. Yeah, that is what I had a video there, but it's not here. Okay, so but you can understand from here that the droplets don't get transported on its own. There must be some fluid flow associated with that, some air flow, some gas flow, something like that. So you cannot only model the droplet transport without considering the airflow. That means you have to take into account the airflow as well as the droplet transport. So that is done using a combined Eulerian-Lagrangian approach. Okay. So what we do, we model the airflow or the continuous I just missed mentioning something. So in the Lagrangian approach, it basically solves the Newton's law of motion, nothing else. So this is momentum, this is force. Okay, it's just that, and the location of each particle can be calculated using dx dt is equal to the particle velocity. From that, you can track the location of each particle.
So here G and AP products.
So these are different type of external forces. No, it might be gravity, it might be something else. So FD is, I think, drag force or something else. I'm not sure. This is the Brownian motion. FD is the Brownian motion because every particle, it vibrates on its own and it can get transported like that. So this is due to Brownian motion. So the same type of equations are used in the Wallerian Lagrangian approach also, but there has to be some coupling between the Wallerian and the Lagrangian approaches. That is done using this particle velocity. So these, the external forces, those are calculated based on inputs from the Wallerian phase. Those forces are taken into account while calculating the particle locations. So these plots at the top, these are images from an experimental study of there are some gas molecules. So this N2, N20 is basically, they have studied nitrogen transport in some complex channels. So this is the concentration of nitrogens. They are imaged from experimental observations. And these are the simulation results using this Wallerian Lagrangian approach. You can see we can actually almost replicate the experimental findings.
So what is XP, sir? XP?
XP is the particle location.
X is the location.
X is the location. Okay. So this is another example from the same that blood flow model that I showed you. So these are the particle locations within the arteries. Okay, model. So within blood particulate phases like the RBCs, WBCs, these are all particles. These are not fluids. So you can track the motion of these particles using this approach. Okay, now the problem with this Wallerian Lagrangian approach is that if you have a large number of particles, then it becomes difficult to track the particles individually. The reason is that while we are solving, you have any idea about CFD or something? You have any idea? So in the Wallerian approach, what is done is that the sample domain is subdivided into a number of small divisions, and so those divisions are the control volumes, and for each control volume the conservation equations are solved. Okay, so if we have a large number of particles, we have to solve the conservation equations for those number of cells or volumes. In addition, we have to track the location of each particle individually. So it becomes very computationally expensive. So we will require very high-end machines. We will require a long time to simulate. Those type of difficulties arise there. So in order to overcome these difficulties, we can always use the Wallerian approach. What is done in the Wallerian approach? The continuous phase equations are similar. Okay. Define a particle concentration for that volume, and we can track the change in the concentration. So this is the concentration transport equation. Okay, and we can take into account different forces and everything here also. Like we did in Lagrangian approach, here also it can be done. So I've shown one example here is that there is some particle concentration at the inlet of this duct. Okay, so this yellow is higher concentration, blue is the lower concentration. So there is some fluid flow happening, and with that, with time, the concentration is spread towards the end of the duct. Okay, so two samples times have been shown. This is at a lower time, this is at a higher time. You can see the shift in the contour legends here. Okay, so now that there is a debate about which approach is better, the Eulerian-Lagrangian or the Eulerian approach, or for which conditions these type of approaches are valid. So this is, I have taken this from one paper. They have shown that when the particle concentration is low, for example here, then there is large deviation between the two approaches. So these dotted are from the Lagrangian approach results, the continuous line is from the Eulerian approach. You can see there is a large deviation. But as the particle concentration increases, you can see it's the both similar results. So whenever there is a large concentration or large number of particles involved, we can always use the Eulerian approach. Okay. So this is another example. This example is basically a flow in an alveolar region of the lung. So this spherical space or the spherical volume is the alveolar region of one alveoli. And this is the duct which is connecting the alveoli to the rest of the lung. So there is some concentration here. Okay, you can understand the concentration profile from here. This is a higher concentration, it is getting diffused here. And from these two plots, you can see the particle location as well as the concentration of the particles. Okay, you can see that it is almost similar. So we can use both approaches, whichever is suitable for us, or based on what parameters we want to observe, we can choose whichever approach is better for that. Okay. So these type of approaches have been used for studying different types of phenomena, right from blood flow, gas exchange in the lung, drug delivery in the lung, drug delivery in the blood flow, all those type of things. Yeah.
So to discuss this, the challenge that is coming into this alveolar is the fluid is outside air.
Yeah. So there are some particles embedded or particles that are carried by the air. For example, if we inhale some particles, the pollutants if we inhale with air, so if that reaches the alveolar region, that is bad for health. So these studies try to model that type of thing if the particle is reaching the alveolar region or not.
And there will be a kind of boundary. The boundary is not solid boundary, right? For alveolar.
Right, yeah.
Then the
So
gas
these
exchange.
boundaries are solid, but we can also model gas exchange. We can model that.
In reality, this exchange.
Yeah. Gas exchange, but it can be done at this work that I showed you. Consider gas exchange in this.
So this will be a good study for smokers as well.
There is a lot of study on this, right from 1970s. Lot of studies are there. But yeah, mostly they have considered the upper branches of the lung, but the alveolar regions, because the length scales are smaller there, not much studies are available for that region. Okay, so as I was talking, these approaches can be used to study lung ventilation, by ventilation meaning gas exchange. So how much gas is being inhaled and what is the distribution of the gases like nitrogen, oxygen, the distribution of these gases within the lung. It can also be used, as I was talking, to understand particle transport. So let's talk about a particle transport in a bit detail. So this figure, it shows airflow velocity in this half and the corresponding particle locations in this half. Now, what are the important parameters that need to be considered while modeling air and particle transport together, or any fluid and particle transport together? First is the Reynolds number, obviously. So everyone knows what Reynolds number is. Second is the Womersley number. Womersley number is equivalent to Reynolds number for pulsatile flows. By pulsatile flows, we mean when there is some definite change in the velocity direction with some time period. Like we can model airflow or breathing patterns using a sinusoidal curve. We can almost model, approximate that. Okay, so Reynolds number and Womersley number. Third one is the Stokes number. Any idea about what Stokes number is? The Stokes number is basically ratio between two time scales, the particle time scale and the flow time scale. Okay. By particle time scale, we mean the time taken by a single particle to reach a definite position. That is the particle time scale. And flow time scale is, we all know, velocity and distance. We can use that to calculate the flow time scale. So Stokes number is important. So a lower Stokes number means time to reach the flow time scale. Okay. And the reverse happens when the Stokes number becomes high. So when a Stokes number is low, the particle, a single particle, it tends to follow the flow trajectory. But when the Stokes number is high, it does not follow so. And it can deviate from the streamlines of the flow. Fourth one is the Brownian motion. As I was telling you, the Brownian motion, all particles undergo some Brownian motion, and we can model Brownian motion based on Einstein's, some relation is there. We can use that. I will show you later. Okay, so these parameters need to be considered. These are the parameters that have to be considered. We cannot ignore these parameters. There may be other parameters also, but these have to be considered. This is the similar as I was telling about the blood. Okay. Now, when a particle is being transported with flow, it can be any type of flow, there will be particle deposition. So, how does this deposition occurs, or why this deposition occurs? That is due to the influence of external forces on the particles. There may be a large number of forces acting, but for applications for which I was showing you, the major parameters are this one, inertial impaction. Impaction means when a particle, while it is flowing, it is impacting onto a wall or surface. So when the Stokes number is high, the inertial impaction is also high. Okay, because it can deviate from the flow stream. It can deviate from the flow stream, and it can hit the wall here, and it can, once it hits the wall, it gets stuck there. Second one is gravitational sedimentation. Whenever there is gravity, it will act differently on the fluid and the solid particles, and there will be some differences in gravitational force which can cause you to deposit. Third one is the Brownian diffusion. Brownian diffusion is important when the flow is very slow or almost stagnant. When the Reynolds number is close to 1, then the Brownian diffusion dominates. Okay. There may be other type of deposition also, like electrostatic deposition, the interception. We can also get particle deposition using magnetic force. Okay. So I will just talk about these three types.
So in inertial interpretation, you mentioned that the particle will hit the wall and deposit over there.
Yes.
So why so? It's not that it will bounce back.
No. Okay. What happens is that in case of lungs or blood vessels, there is some fluid layer, some different fluid layer on the walls of the inner walls of the lungs and the blood vessels. So it gets stuck in those fluids. So those fluids are non-Newtonian. So those fluids are non-Newtonian and viscous fluids. So if the particle gets hit, or if the particle hits, it slows down and it gets stuck there. Not that it may not, or it will be stuck there forever. It may get again transported due to airflow. But for the time scale we are considering, which is very short, it will get stuck there.
So the impact is not that much elastic impact.
Yes, yes. So these walls we are considering, these are all elastic walls. Okay. This is what I was talking about. So this is an image of the mucous membrane on the inside of the lung. So this is the the lung wall. On that we have something called cilia, and on top of that we have the mucous layer. This is the viscous non-Newtonian fluid. If anything, if any type of foreign substances are inhaled, they get deposited and stuck on this type of things. Okay, but interestingly, there is some inbuilt mechanism by which this mucus moves. It is not stagnant. So, in case of the lung, the mucus flow is upwards towards the mouth. So if anything is deposited there, it will ultimately cough, sneezing, and so by those mechanisms, it will be ejected out of the system.
So that is also you will say another kind of fluid flow and there is downward
Exactly.
some kind of force.
That is what I was coming to. So we have to consider, if we have to realistically model these phenomena, we have to consider particle clearance also. So ultimately we will have three phases. One is the fluid, one is the particles, and the other is this fluid. Okay. So you can understand how complex this type of things are. So in order to reduce the complexity of this type of modeling, we can adopt something called reduced order modeling. By reduced order, we mean simplifications of highly complex models. But at the cost of reducing the complexity, we also have to compromise the accuracy. So there must be some trade-off between the accuracy and the complexity. But this type of simple models are helpful in identifying the dominant effects in a system. But we must be careful that the underlying physics of the phenomena should remain same. If the physics get changed, then everything changes. Okay. So I will give you some idea about what that I have done, and it is some part of it is already published, but some part is under review. So I am not sharing all details. I will give you some idea. So let us consider a lung structure that I was talking about. Okay. Now, it has been observed that the lung structure, it bifurcates into two daughter branches at each generation. So from here the main branch is subdivides into two, from here it again subdivides into two, and like that. So 23 generations, and these are the number of branches per generation, which we can model as 2 to the power n. N starts from 0. So for the first branch there is only 1, from the second there is 2, and like so on. And we have the length and the diameter for each generation branch also. Okay. But the interesting thing here is that we can only assume these things if the branching is symmetric. If there is some asymmetry involved, we cannot do this. Okay. So the first assumption here is that the branching is symmetric. Now what we have done is we have approximated the length and the area. From diameter we can get area. The length and area at each generation using a power law function. Okay, so the L naught is the length at the first generation, A naught is the area at the first generation, and we have assumed two factors, alpha and beta. These are the length change and the area change factors, which is a function of the generation number. So, if you do that, we have observed that we can approximately match the experimentally observed length and area pretty well. So, the red one is the actual data from experiments or the physiological data. The blue one is from our work. There is some deviation at the last two generations, which I will tell you. The black one is also done by us, but for a okay, and we have approximated this deviation using or considering an additional area in the last two generations, okay, or the last few generations. So with that, we can approximately, get a reasonable agreement with the physiological lung structure. Now, once we do that, we can consider that for a symmetric type of structure into something like this. So this is a variable area, not only area, variable length and area channel. Okay, where the inlet or the throat is at n equals to 0, and the alveolar region is at n equals to 23. Okay.
Equal to 17 to 20. So
Yes. So it ends at 23. It starts from the 17.
sir, one question is that this complicated structure. So possibly it is not done manually in the CAD.
Yes, from CT images we can take.
CT images
We can import into CFD software.
that is directly in your brain.
We can do that. Okay. Now, as I was talking about, we have to also consider particle clearance. In order to do that, we have considered a layer, this mucus layer within this region, the inner side of this region. Okay, but the useful thing is that we don't really need to construct this model. We can directly solve. We can directly solve the equations using area and length parameters. Okay. So first, one thing I missed. So this type of model is called trumpet model because this shape is like a trumpet.
Sir, how do you just simplify the complex model in this manner?
Yeah.
Is there any assumptions or something?
Yeah. That's what I told. The first assumption was symmetric branching. Right? Second, we matched the area and length change, this thing, using these relations with actual data. Right?
Sir,
So basically fluid flow, it depends on the geometry. If we can approximate the geometry in a simple manner, then the flow physics remains same, right? So that is why we can approximate. I'm not telling that we can replicate this thing. We can approximate this complex thing into a reduced, simplified geometry. For example, I will tell you, if we have to solve the fluid transport and clearance equations for the whole lung geometry, no one has done that. Not even today. Okay. So what people have done is they consider either the upper branches or the lower branches, but not together. Because it is impossible. If you see the number of generations here, it is impossible to solve. That is why these type of simple models are used.
We are also assuming that it is kind of all over the place. It's right.
Yes.
We are reducing it to
Into simple channel, but it at with
area.
replicated length and area.
So one thing, the main branch, obviously the flow storage will be high.
Yes.
And as the branches came out from there, obviously the flow rate.
It will reduce.
But here, as per the model, you have this type here. In the half sections it is low, section level is low, and whenever it is gradually coming down, the area become more. How is it possible?
I mean, the wall effect is.
If you consider the number of branches at each generation, for example, generation 3. So here we have one branch, we have 8 branches here. So the flow through a single branch, it is getting subdivided into 8 branches, right? We are considering, okay, first tell me why the flow velocity will reduce if there is subdivision. So if we take into account all the areas together, the same thing will happen. Right?
Possibly the only deviation that we are considering is the in actual case there are in number of these perimeters. Here we are reducing the perimeter. If we just take one.
Yes, exactly. Okay. Okay, so with that, we have to solve the fluid dynamics equation. So these are simple fluid dynamics equation. I'm not going into detail. Okay, only the mass momentum equation. Only thing is that since the area is changing here, we cannot take area out of here. So we have to consider area.
Sir, the flow is obviously laminar.
Yeah, I will tell you. So this is this thing. Okay. Second point is the Reynolds number. Reynolds number remains high at the inlet, close to 1000, which is laminar. It is not turbulent. In the mouth, when we inhale, it is somewhat turbulent. As it goes into the lung structure, it is laminar. And this at the it is almost as it is. And this change or this reduction in Reynolds number, it is after generation. Okay. So you can understand that from here we can neglect this inertial term because the flow is so small or so what should I say slow. We can neglect the inertial term here. Second point is that in case of breathing, the flow is sinusoidal. We have to consider Homer's number, but Homer's number is also very small. So the flow we can consider as quasi-steady. After if we start breathing suddenly, then there will be some transients, but after a short time it reaches a quasi-steady state. Okay. So ultimately, yes.
Extreme right portion that we should take this one.
This is
Pressure.
pressure drop. This is the Hagen-Poiseuille approximation, the reference. Flow resistance. If there is flow through parallel channels, we can approximate the flow resistance using this thing. Okay. So with this we can remove this term. So ultimately there is a balance between these two terms. So we can easily calculate the pressure drop across the whole lung from this approximation. Okay. So the second equation is basically the resistance at each branch. We can calculate that also, or the total resistance throughout the lung. With that, we have calculated or we have compared with some actual data. This is the data field. The optimal one is the actual data. So there is some resistance ratio for which there is an optimal flow distribution in the lung. So that comes around 0.78. With our model, it comes around 0.73. It is very close.
How the resistance ratio is calculated?
Yeah. So resistance ratio is this Rn by total resistance.
Sir, why suddenly increase?
Now, this is alpha. Alpha basically the lane change factor. So for alpha, a particular value of alpha matches with the experimental or actual data. This alpha, this is the same thing as we defined here. Okay, so if we for a particular value of alpha, it will match. So that is why the lung structure will have.
Alpha value after 0.7, it suddenly goes rise.
Yes, yes. Because in that range, there will be some flow through the lung. If the alpha is here or here, there will not be any flow. But for alpha around 0.78 or 0.73, the flow is optimal. Or the flow distribution is optimal. Okay. Second is, as he was asking, gas exchange. We can model gas exchange also. Only we have to consider a sink term. Sink term means there will be some loss from the flow domain. This is the term which we can use. So this D exchange is some parameter we have used to identify the exchange rate, and this is the concentration difference. Cg is the concentration of the particular gas, and Cg infinity is the concentration of the gas in the blood stream. So gas exchange is between the lung and the blood vessels only, right? So we can approximate the gas exchange using this term. Okay. Now this equation I have marked here because we actually use this equation for numerical solution, but we have obtained some analytical solution also. We have derived that because we can neglect the transient term, we can neglect this term also due to inertial this thing. So there is ultimately, I'm sorry, we have not neglected here. We have considered these two terms here. Okay, this thing and this one. So del x of we have combined together and it is 0 with the constraint that there will be some gas exchange at the end. So this serves as the boundary condition of the problem. And we obtain a solution like this, which has basically two parameters, Becquerel number and another exchange parameter Z. So Becquerel number is basically a ratio between advective transport and diffusive transport. So advection due to airflow and diffusion due to Brownian motion. If Becquerel number is high, the flow will be higher, or the advective flow will be higher. So the concentration will be shifting towards the end of the lung, as you can see here. So Becquerel number increases, the flow shifts towards deeper into the lung. Okay, and this change where this slope changes, that actually shows from where the diffusion starts to dominate. Diffusion of the gases. So these two plots are for two different exchange rates, for two different magnitudes of Z. If the Z value is lower, the exchange is the gas exchange is higher because this parameter is in the denominator. So if Z is lower, the exchange is higher. So you can see it from here.
What is Z?
Z is the exchange parameter I defined. Okay. So this Q is the flow rate, A naught is the area at the first generation, D exchange is the exchange rate for the gas. So we have considered some exchange rate. With that, we have obtained a value of z. So this is for two different z. You can see from the scale of the y-axis that for lower z, the concentration drops from 1 to around 0.2, but for higher value of z, it drops from 1 to say 0.9. Okay. So these are same thing for two different magnitudes of z. The same thing is shown here. Now, how do we test if our solution is correct? We have opted for correction. How do we test our numerical solution is correct? So we have used this equation for our numerical solution. We have considered the transient term also. So there will be some time variation for the concentration. You can see it from here that when the flow starts, the concentration is 0. With time it rises and ultimately reaches a steady state within this 5 magnitude. So this tau is the non-dimensional time and it signifies the number of breathing cycles. So if we start breathing, within 5 to 10 breathing cycles, it becomes a steady state. Okay. And this is a comparison between our analytical and numerical solution. The steady state plot, this class basically. So this is the same comparison. What I showed you was only for uniform flow. There was no pulsatile flow. What happens if there is pulsatile flow? The concentration will oscillate like this. If we assume an airflow variation like this, the concentration will also change with time in a similar manner. So these different colors show concentration at different generations of the law. Okay. So these plots on the top are basically if we consider continuous inhalation of a gas or of a gas, because we consider it gas here. But if we say inhale gases for a finite duration, say carbon monoxide they inhale, so it will not be continuous, it will be for a finite duration. So this is the thing. So here we have considered inhalation for only 5 breathing cycles. So it is inhale for 5 and after that this curve is followed. So this type of plots, these are called wash in and wash out curves. So something is getting washed in and that thing is also getting washed out with exhalation. This is with inhalation, this is with exhalation.
So this is x-axis is time.
Time.
So and the location is within the algorithm.
Okay. So we have considered 3 locations. At the beginning, at n equals to 0, at the middle, n equals to 12, and at the end. So time change, the characteristics of change with time is similar. Magnitudes will be smaller. So highest magnitude at the beginning, and as we go down, the magnitude will come down. Now, what if we substitute gas exchange with particle or droplet transport? We can use the same equation. This same equation we were using for gases. Only thing is that diffusion coefficient will change because for gases the diffusion coefficient is different from that of particles or droplets. So this diffusion coefficient will change and the sink term or the loss term will change because here particles will be deposited, not exchanged in the bloodstream. Okay. So here also we have reduced this thing to a non-dimensional form as a function of Peclet number. There is no z term here. We have substituted that with a different parameter, non-dimensional parameter, and we also have Stokes number here because for particles we have to consider Stokes number. Okay. So these are the different equations which we use for modeling the loss term or the different depositions. And we have to, if we consider deposition, we have to consider particle clearance also. So this is done in a similar way as that, as I was talking about earlier. But another equation needs to be solved. Concentration equation similar, but the earlier concentration equation we were considering the concentration of particles, droplets, or gases in air. Here we have to consider the concentration of the deposited particles or droplets in the mucus layer. So these two concentrations are different. And here we had a loss term, this thing. Consider this thing. This will be added to that equation because what is getting deposited will be acting as the source for the this fluid, for the mucus fluid, right? Okay. So with that, this is the curve for the similar type of breathing pattern. This is the curve for particles. You can understand this is different from gases because for gases this change in slope was happening somewhere around here. Okay, and these are shown for different times of the flow. So this is inhalation peak. This one inhalation peak. This is the end of inhalation. This is exhalation peak and end of exhalation. So you can understand that what is getting transported into the lung, most of it gets washed out. Okay. We can also calculate what is the amount of the particles or droplets that is getting deposited at each generation. This is the curve that we get. The SD is the total amount of the particles or droplets getting deposited. Okay. So we have considered in order to validate the model we had, although it is a reduced order model, it also has several complexities there. Right? So we have to validate our model. This is done by comparison to experimental deposition data. This black one is the experimental data. This is considering the whole lung, the complete lung structure. This is only for the alveolar region. And for x-axis we have particle diameter.
Experimentally, how
Yeah. Experimentally, they have what they have done. They have considered straight tubes, straight metal tubes or plastic tubes of different diameters, and they have carried out the experiments for different cases. They have added together this data. But this data can also be obtained using imaging. If you take there is something called gamma scintigraphy imaging. If we use gamma scintigraphy, we can actually have an idea about what is the amount of particles or any other material that is getting deposited within the lungs. Okay. What we need to understand here is that deposition is not uniform for all particles. Right? So this is the total lung deposition, which is maximum for higher size particles. 100 particle up to 10 micron it is higher, then it reduces to a minimum and then again increases for smaller particles. That is because for this range, it is not getting inside the lung, it gets trapped in the nose or the mouth. If it gets into the lung, this deposition, this part of the deposition, it takes place mainly due to inertial deposition mechanism. So large size particles have higher mass, higher momentum, and they get deviated from the flow easily. Right? So inertial impaction or inertial deposition takes place for this region. Diffusional deposition takes place for lower size particles. For lower size particles, diffusion is more as compared to higher size particles. So diffusional deposition dominates here. In this region, there is a combination of these three. But if we consider the alveolar region, which is our main focus, because gas exchange, health effects, everything happens if foreign particles reach the alveolar region. So for this region, there is two peaks. You can see one is here, one is here. So this is around 3 microns, this is around 20 nanometers. Okay, so if particles or droplets in this size range gets inhaled into the respiratory tract, not trapped in the nose or the mouth, then it becomes possible to have severe health effects there. Okay, so these are some results. With different platelet number, we get different type of deposition as I was showing. This is for different breathing time. There is another parameter, HT. This is called the Struhal number. Struhal number is nothing but the ratio of two time scales, the airflow time scale and the diffusional time scale. Okay, so if we change that, we actually get a change in the breathing time. So this is non-dimensional, but physically we get a change in the breathing time. So for a lower Struhal number, we have a larger breathing time. It means that if we inhale for a longer time, the deposition will be more. Okay? You can get it like that. This is for longer exposure. Means we are inhaling for a long time. This one for a longer breathing period of one cycle. So each breathing cycle is longer here. Here we are considering same breathing cycle, but for a longer number of breathing cycles. Okay, the similar type of thing happens here. So I will not talk about much further. Only there are two applications that we have considered that I will show you. And I will stop. But there are many more applications that can be started using this type of models. The first one is drug deposition and retention within the lung. So pulmonary drug delivery is a very research topic, and research is going on still to increase the efficiency of the delivery, because whenever we inhale the drug molecules or anything, it gets deposited mainly in the nose and the mouth. It does not reach the deeper lung. But these drugs to have effects, it has to be visible. So this paper is published, you can see. So let's consider inhaled drug dose per puff of an inhaler. With inhaler we puff, for each puff we have 100 micrograms which is being inhaled. So we consider different particle sizes or aerosol sizes, and for the same this thing, we can see that only if the aerosol size is around 20 nanometer, the enhancement is very high. For 3 micron, this is around 2.8. So from 100 micrograms being inhaled, only 2.8 micrograms can reach the data. Okay, so the rest is actually lost. But if we reduce this to 20 nanometers, it increases to 3.95, like that. And for other size ranges, it can either reduce or increase. But if we increase the breathing period that I was talking about, then we can have significant increase in the amount of drugs reaching the lung, the deep lung. Okay. So interesting results that like this can be obtained from this type of studies. The second one is pathogen infection. For example, COVID or SARS-CoV-2. We validated our model. This is under review, for which I am not showing all results. So these black dots are viral load or virus concentration, let's say, from hospitalized patients. Black dots. And this red one is our prediction of virus concentration with time in days. You can see that we can approximate the trend that it will follow. These are for two different cases. Okay. Important thing is that, although I am not showing the result here, that virus or any type of infection, pulmonary infection, it becomes severe only if the virus concentration or pathogen concentration reaches a critical limit. Okay, so for SARS-CoV-2, this limit or the critical value for pneumonia onset. If pneumonia onset happens, then it becomes severe disease. For that, this was around 7 into 10 to the power 6. Okay, so it reaches like this region. And here also like that. We have also obtained some other interesting results, but I cannot show it right now. Okay. So let's stop here. Okay.
Okay, thank you, sir, for this very informative talk. So now the floor is open for questions. So if you have any question, please.
Sir, while blood is flowing,
Blood. Yes.
the sources from the heart is pumping. Yes. Obviously, so the intermittency will not be a continuous. Then how can
It is not intermittent. There is some particular characteristics of I would say time characteristics of the flow. It is not intermittent. Like on off like that. It is not.
volume product
Small volume fluid remains. It is not a sinusoidal flow, but it is not like an on-off flow also. Yes.
You have cited some papers of others
Yeah.
as well as yours.
Yeah.
So, did you carry out any experimental?
No, actually we planned to when I was doing my postdoc in IIT Madras, but due to this pandemic, it could not be carried out actually.
So, your work is purely numerical.
This is purely
So,
theory.
did you develop any code on your
Yeah.
work?
So this reduced order model that I was showing, this is MATLAB code actually. MATLAB code, and the earlier result that I was showing from my own lab, those were carried out using ASIC.
I was thinking that we were taken any energy conservation.
Yeah, so we have not considered any temperature or heat transfer yet, so we have not solved the energy conservation, but it can be done.
Any other questions? Sir, the first one is at the beginning, if you go to the beginning of the slide, the small question that I give you on the floor. The Eulerian approach.
This one?
This one. So here you have shown three cross sections. So these three cross sections and this channel cross section is from the middle and base.
Yeah.
So these three cross sections at the middle we can see raised and regions.
Yeah.
So that is so that
This is boundary layer. Basically, a boundary layer is formed. Maximum fluid velocity is at the middle.
Yeah, what I am saying is that we can see the raised and here.
Yeah.
So then if you are taking a cross section from the middle, then we should
Okay. So these legends are most probably not similar. From this and this. This is not my own work. That paper. Most probably that is the reason.
Yeah. One more thing is that we have mentioned in the next slide, and also during your own work that we have obtained the three-dimensional model, analytical model, directly from the city.
I have not directly used that, but it can be done.
Yeah, so I'm curious that whether you are getting that model from the
But there is some
there
other
are many software. So I mean,
not image analysis software. There is some specific software, open source software, which can be downloaded and you can import the city images and reconstruct the model.
yeah. So that you have done yourself.
No, I have not done that, but it can be done.
Okay.
I don't know. You can search it, it is easily available. Okay.
Okay. Any other question? So if there is no other question, join thanking Dr. Chaturvedi. Okay. So we are almost at the end of our today's session. So before ending, we like to felicitate two of our speakers. So
এটাকে নিয়ে নেব।
So please come.
একটা ভিডিও চলছে স্যার, মানে যে পিপিটিটা শুরু তো ভিডিওটা শুরু এটা হচ্ছে ফ্লুইড এন্ড পার্টিকেল ট্রান্সপোর্ট কমপ্লেক্স। অ্যাপ্লিকেশন বায়োলজি তো আমরা জানি পড়া যায় তাহলে সেটাই সলিউশন সিস্টেম আমি এটা জাস্ট এক্সাম্পল দিচ্ছি, পরে আরো কিছু আছে।